Okay, I've got the stream going now. Welcome back, everyone, to the discussion session, which is the second half of the first day of Capra. Without further ado, I'm going to turn it over to Niels Warburg, who will be hosting this, chairing this discussion.
Thanks, Aaron. Let me just share my screen. Has that now gone full screen?
Yes.
Great. Okay, so thank you very much for being invited to lead this discussion. I think this is a great part of Capra, the discussion sessions. So we'll see how that's going to work in the virtual environment. What I thought I'd do there before we kind of open for more discussion or having smaller discussions is just give a brief overview of where we are at first order, in particular, what is it we need to do? What is the status of those calculations and what challenges do we face? I'll then take the opportunity to just give a brief update on the black hole perturbation toolkit. Seems like a nice spot to fit this in. So just a 10-minute update on that. And then I'll just probably quickly just overview Slack in case anyone isn't familiar, but it really is a great way to have these discussions in this kind of virtual arena. We used it for the Black Hole Perturbation Toolkit workshop, and it was great for text-based discussion, but also for arranging smaller little discussions between smaller groups, as you might do in a real kind of Capra conference where you wander off and find a room and a blackboard and talk about something. So I'll kind of highlight that. So I'll probably take up somewhere like 20 minutes, 25 minutes just to go over some of those details and some ideas. But after that, what I thought I'd do is, if you're interested, then there'll be smaller discussions that I'll arrange. I'll post a link, a Zoom link probably into the Slack. And if you're interested in these following topics, then you're very welcome to join, just to listen in or to contribute as you would in a regular meeting. And those additional topics are going to be faster GSF codes. How do we actually make those codes faster? And that isn't just for numerical people. That's also people who are interested in the techniques that how you might use to actually compute the GSF. That might be faster techniques in an actual implementation. As you'll see, a big challenge we're facing is covering the parameter space. In terms of, sure, we need faster codes, but we also need to smartly cover that space so we can run those codes as few times as possible, especially in the sort of generic configuration. And also, of course, we're starting to see actual people talking about waveforms at Capra, which is great. And so I'd like to bring that up as well. Great. Okay, so what do we need at first order? Just quickly review it. So for adiabatic inspirals, not talk about waveforms at this point, just the inspiral. What do we need? Well, we need the fluxes for a point particle on a generic bound orbit in Kerr spacetime, and we need to cover and interpolate that large parameter space. If we want to go beyond adiabatic inspiral and include subleading corrections in the phasing, sort of GSF inspirals, then what we need is a first order gravitational self force for every point of a generic bound orbit in the Kerr, about a Kerr black hole. We're also going to need fluxes, the perturbation to the flux basically due to the spin on the secondary, again for generic bound orbits in Kerr. And as it's going to be a common theme, we're going to need to cover and interpolate that parameter space. Something we don't talk about so much, but I guess we'll talk about more tomorrow in the second order sessions. To do second order calculations, we need first order calculations, we need first order data. And so in particular, we need the first order metric perturbation stored on disk everywhere in the space-time for generic bound orbits in Kerr spacetime. So there's a lot of data that needs to be stored there and curated. Another thing we need in order to do the second order calculations or the near identity transforms is you need the derivative of the metric perturbation with respect to the orbital elements, so with respect to P or E or the inclination of the orbit, again, everywhere in the spacetime. So I'll discuss the state of that in a moment. And then finally, for waveforms, well, what do we need? Well, we need those waveform amplitudes that we heard about in the last two talks. And again, obviously for bound generic orbits, and again, cover and interpolate the parameter space. And then finally, we need a computational framework that really brings all of these together and uses all of these pieces to actually produce waveforms rapidly. So what I thought I'd do is just going to go over the status of each of those 4 or 5 things to see where we are and what we actually need to do, and hopefully to set some topics for the discussion that will come later. Okay, so for adiabatic Ian spirals, what do we need? Well, we need fluxes for point particle on a generic bound orbit and Kerr. And since sort of mid of the last decade, we've been able to do that. We can compute those numerically. I also understand we have analytic results from the PN, from the Japanese group and their collaborators, as well as we have some other analytic results in the near extremal near horizon regime, which I think could also be useful. So we certainly can compute these things, tick. That's something we can do. It's generally not too slow. We have sort of C implementations of the numerical codes. Obviously, the PN series can be evaluated very fast. We can always try and push those to higher order, but they're certainly useful as they are. The main challenge, I think, is covering the parameter space. As I said, that's going to be a recurring theme. I don't think running the codes to cover the space is too bad. I mean, we've got plenty of time before Lisa launches. We have codes, we can just run them. But there is an issue about sort of high quality interpolation. So in general, if we want to add on sub-leading corrections, we need the leading piece, which is the dominant contribution to the phasing, needs to have very accurate flux information. And in general, the residuals need to be less than 1 over the mass ratio. So we need very accurate data, and then we need to interpolate to a very high level. So maybe 10 to the minus 6, 7, or 8 relative precision in order to drive those in spirals. And so that's an open challenge. And also how and this again will come up repeatedly, how to cover that space smartly. So in the past, what we've done is we've just gridded that space because we've just done something in Schwarzschild or equatorial orbits. But this isn't a clever way to do things. There's obviously a better way to space the calculations. We haven't had much emphasis on that recently, and that's something we really need going forward. It also seems very natural that we should blend the analytic and numerical results. So a natural thing to do would be to subtract off all the PN results that we know, and then just fit the residual numerical results to try and reduce a numerical error. Likewise, in the near horizon regime for rapidly rotating black holes, you can do the same to help kind of inform our fits. I think there is a lot to be done there. And I think it's probably a little bit tedious. That's why people haven't looked at this, but it is very important work that we need to start doing. And there's also some very interesting theoretical questions like how do you cover that space well and interpolate it well. I think in terms of gravitational self-force in spirals, as I said, we need the first order GSF for a point particle on bound orbit and Kerr. And we also need the correction due to the spin on the secondary for bound orbits in Kerr. And as always, cover and interpolate that parameter space. So where do we stand with those? Well, with first order gravitational self-force, we can now, since 2017 or so, Martin's paper came out, so we can compute this for any point in the parameter space. But the current implementation, the one implementation we have in the community, and Martin would admit himself, is very slow. It's written in Mathematica, takes a lot of CPU time. And the reason for this, you need one is written in Mathematica, and you also integrate in many more modes than you would need for a flux-based calculation, because in order to do the regularization, you need a lot of extra precision. And the convergence is not as rapid as you get exponential convergence, you get power law convergence. So that's very slow. So there's obviously huge scope for sort of the kind of stuff that Michael was talking about, like speeding these calculations up in terms of C implementations, GPUs, and we really do need it here because these calculations are expensive. And so that's something we should talk about in the discussion, how we might do that. All the better calculation techniques we could use. I've written here there are no PN series as yet. As far as I know, most people compute PN series for the fluxes or the gauge invariant quantities. I'm sure they could quite easily compute at least radiation gauge self forces. That would be useful, I think, in terms of even just for circular orbits or eccentric equatorial or something, because that will help inform the fitting and stuff we have to do to cover the parameter space. In terms of spinning bodies, where do we stand with that? So as far as I know, we only have results for circular orbits in the equatorial plane of a Kerr black hole. We have those results numerically, which is very nice. And we have some PN results as well, although I'm not sure we have Kerr PN results, perhaps just Schwarzschild, but people can correct me if I'm wrong there. I had to Google around. I couldn't see anywhere that people had done eccentric orbits, let alone sort of generic inclined ones. And so I think there's a lot of development that has to go on here. But I see a lot of interest in the community recently. I've seen a lot more talks at Capra in the last few years about contributions from the spin on the secondary, and so it'd be great to see more of that, and we certainly need it. Again, recurring theme, covering the parameter space. This has only really been done in Schwarzschild. We've never attempted it in Kerr. I know Scott Hughes has been running some data, but we haven't played around with that very much. And even then, it would just be for one spin value, probably not very dense. That's been done by gridding. And again, we need a smarter way of doing things than just gridding things up. The one saving grace is perhaps we don't need this to such high accuracy because it's a subleading effect. You don't need to interpolate things to 1 part in 10 to the 7 or something. A relative accuracy of 10 to the minus 4, 10 to the minus 3 even you might get away with. And so that actually allows a lot more of the parameter space to be covered with analytic methods, with post-Newtonian fits or inspired fits or resummed fits. Again, near horizon expansions in the deep strong field could be useful. And so there's a lot more scope there for blending between the PN results and numerical results to cover that part of the parameter space. And so I think that would be great to see. I actually realize I've left off the second order piece, so I'll just go back and talk about that. So for second order, yes, we need the vector perturbation everywhere in the spacetime for bound orbits in Kerr. So in principle, we can compute this. We don't have codes that actually output this data yet, at least in the radiation gauge. In terms of the derivative of the metric perturbation vector orbital elements, we have this just in one case, because that's the case we're looking at second order. So we have this for circular orbits in the Lorentz gauge. So the derivative of the metric perturbation with respect to R0, the circular orbit radius, is something we do have, but this will need to be extended to more generic situations in the future. So those codes don't even exist yet. So that's something we'll need, and they'll again need to be fast in order to cover the parameter space. Yes, okay, so waveforms, where do we stand there? So as I said, what we need is the waveform amplitudes for, again, fully bound orbits in Kerr and to cover that parameter space. In terms of computing those amplitudes, yep, we can do that. The Tucholsky amplitudes or Reggie-Wheel amplitudes, we have those numerically, and we have PN fits for those. Again, we don't need high precision. The error in there doesn't accumulate. It's just an instantaneous error, so leading order amplitudes are fine, as Alvin mentioned. And again, we need to cover and interpolate the parameter space. And it's a similar challenge to the GSF. It doesn't need to be to very high precision, as Alvin and Michael showed with our work. We can get away with, interpolating with neural networks. Yes, the precision might be about 0.1% in the amplitude or thereabouts, but that seems to be enough for that. And maybe some of those techniques then would be enough for certain pieces of the GSF as well, and that's something we should think about. So I think those are the main pieces that we need that are that go into the calculation at first order or feed into a second order calculation. As you can see, some of them we have, and they're just slow to compute. Some of them we don't have. We're missing the spin calculations, derivatives respect to the orbital elements. Covering the parameter space, as you see, comes up constantly. It's not something we've looked at so much, and there's definitely probably stuff we can learn from other areas of the gravitational wave community who have looked at this sort of stuff. And then on this last one, with waveforms, we're just starting to produce waveforms, and I think the framework presented today, as well as surrogate models, perhaps with different mass ratios, those will be those seem to be fit the deal. The cat had to leave. So, okay. So in terms of frameworks, so Michael had this nice plot of a framework that we're going to sort of add to the black hole perturbation toolkit in the next month or so, and we think this is a potential framework for future calculations. As he emphasized, a key idea here is that we want to produce a waveform in a format that the data analysts can use, and then we can just keep changing the back end, and they don't have to worry about the changing of the formats. And so what, particularly, I think the big step forward in that work is the amplitude, the rapid amplitude generation and waveform creation. And as Michael pointed out, a key point of this framework is you can just switch out various modules for other things. So as we compute more gravitational self-force information, we can then compute new fast trajectories. And then as soon as you have that, 10 minutes later, you can have the waveform associated with it, and you can maybe go ahead and do a PE study or something. So here in this diagram that says gravitational self-force, but there's more than just that to EMRIs, of course. As we heard today, there are talks about environmental effects, whether that's third bodies or accretion disks. If you have a fast model for that in Schwarzschild right now, we could plug that in, and in a day or and very quickly we'd have, fully relativistic waveforms with that new phasing correction in. And so I think that's something really nice to see. Likewise, you could also have corrections from non-GR effects. So whatever your favorite change the curve metric is, or if you've got some dark matter halo or whatever it is you're interested in exploring, if you can tell us what the phasing correction is, we'll then just be able to plug it in to this model very quickly and produce waveforms that, again, you can go ahead and use in PE studies, or indeed actually with the detector data. So I think that's I think it's really great to see something like this. It might not be the ultimate framework, but I think it's great to start to see that appearing. And this was something that was called for in the LISA working package document when it was first released, the Edinburgh document a couple of years ago. And so it's nice to see that this is an attempt that has been made to produce that framework. Okay, so I think I'm also going to do a little overview of the toolkit, and I think one of the reasons we started the black hole population toolkit is that it's probably going to be key to overcoming some of these challenges, because you see there's quite a lot still left to do, just a first order, let alone second order, which we'll talk about tomorrow. And I think key to overcoming some of those challenges, we're sharing codes between us, and sharing data as well, and coming up with common data formats. And as just an example, I think until very recently, basically until the toolkit came into existence, there were no public Reggie Wheeler or Tucholsky codes. People have been writing these since the 60s and 70s, but they'd all just done it to themselves, and it's private within their group, and they weren't shared and publicly available. And so the toolkit is addressing this, and so it tries to bring together not necessarily all the leading edge codes, but many pieces of them that help us move forward as a community. Of course, people still keep hold of their cutting edge codes for their research, but over time they filter bits of that back in to the toolkit, and it's great to see that happening already. So if you don't know already, then you can go to bhptoolkit.org and you'll find the toolkit and the various pieces, and I'll just give a very quick one-page executive summary of that. So if you are interested in the toolkit, you will find things like spin-weighted spheroidal harmonics, calculations of that in Mathematica, in Python, in SageMath, code for computing geodesics, again in Mathematica and Sage, quasi-normal mode codes in Python and C Mathematica. You'll find codes to compute the Reggie Wheeler solutions, both the homogeneous solutions and also the source by a point particle in the case of circular orbits at the moment, Tucholsky codes, for arbitrary spin weight. You also find codes for computing in-spirals, so you want to rapidly compute an in-spiral like that Phil talked about, these new identity transforms. You'll find waveform codes, the kludges that Alvin and Michael talked about or alluded to in their talks, snapshot codes, as well as the surrogate codes. We'll hear a nice talk about those on Friday or Thursday, I can't remember. As well as there's a couple of there's a new self-force code in there that's appeared recently. And in addition to that, there's also data, and that data is both numerical data, so numerically computed fluxes or self-forces, as well as analytic data. You get these huge PN series that we derive in our community, up to 22 PN. You put it in people don't often even put them in papers, because you end up having a 75 page paper where 70 of the pages are just the PN series. And often these were just held on people's hard drives. You had to ask for them, but the toolkit brings a way to bring together some of those analytic expressions. So that's very useful for some of this covering the parameter space stuff, I think. And I thought, just to give an example of how far the toolkit has come, I thought what I'd do is just quickly go through the talks that I'm aware of in Capra this year, which use the toolkit, because it's actually substantial. Oh, before I do that, I will just say we did hold a workshop recently. It was going to be held in Prague. Of course, that was cancelled, and we held it virtually. We originally expected about 30 people to attend the face-to-face in Prague, and when we took it online, we had spectacular attendance. We had about 110 people on Zoom, about 20 on YouTube, probably very similar to what we're seeing at Capra now. If you missed that and are interested, the talks were fantastic quality. The speakers put a lot of effort into developing material that helped you kind of practice or get to know bits of the toolkit. And that's available on the Toolkit Workshop website. And all those talks as well were also recorded, and you can go and find there's a YouTube channel, the PHP Toolkit YouTube channel, that has all those talks if you're interested in learning about that. And you can also find it on the Toolkit website, PHP Toolkit/workshops. And I'll give you a link to the YouTube channel from there. Okay, so as I said, which bits of which talks are already starting to use the toolkit, and even just today was actually the most busiest. So Teo said in his talk that he used the Tucholsky package to compute the homogeneous solutions. And then since the toolkit workshop, he has added the electromagnetic source back into the toolkit. So you can now compute the radiation from an electromagnetic particle orbiting a black hole. Leanne, in her talk, some of her work on the MST has made it back into the toolkit, and she'll have used that. MST and Reggie Wheeler has made into the toolkit. Some of Phil's work in terms of calculating four velocities, as well as a new package on oscillating elements, and eventually his NIC calculation will also go into the toolkit. Zach talked about resonances, and since the workshop, he's added a resonance finder into the Kerr GD6 package. So that'll be merged into master soon. Later in the day, as Alvin and Michael said, our goal is to add this new framework also into the toolkit and hope that can get used for ever more, the future kind of framework for MRE calculations and waveform generation. Just to sort of hammer home the theme, for the rest of the week, Adam will be talking about progress towards second order post-update waveforms. Many bits of that calculation use little pieces of the toolkit here or there, and certainly one of our major goals for second order is to open it up soon, hopefully. We have developed a lot of code and data we want to open up to encourage other people to attempt second order calculations to reduce that barrier to entry, which is what the toolkit's all about. Ben will be talking about second order self-force calculations or techniques for that from eccentric orbits, and so he's used bits of the toolkit as well as contributed back a hyperboloidal Tucholsky code in the frequency domain, which is looking very nice and will again be merged into the master branch soon. On Wednesday, Chris Moon will be talking about high order PN series, and all those great PN series that the Chadwick Hall group has produced are now available, and you can load them just quickly in Mathematica because they're all in the toolkit. Ollie Long will be talking about self-force on hyperbolic orbits, but hyperbolic orbits were missing from the toolkit, and those have since been added in collaboration with discussions with Beatrice and Martin. Again, this continues throughout the whole thing. You can see how much the toolkit is starting to touch throughout our community. Peter Diener has added recently his discontinuous Galerkin code, so time domain code for doing self-force calculations, scale at the moment, but I'm sure Sam Cupp will tell us something about progress towards the gravitational case. The UMass Dartmouth group has got this nice surrogate model for more kind of intermediate mass ratio in spirals. And so we have two talks on Thursday from Nur and Tusif on that. And then finally on Friday, we also have talks relating to spinning bodies. And so Josh, I know, has used the toolkit and will contribute bits back, as well as a resonance finder he himself wrote. And Gabrielle will also, it's a nice example where they use the toolkit to solve the Tucholsky equation. And then once they've finished their calculation, they donated some of their data back into the toolkit for others to use as well. So as you can see, it's really getting used quite widely in the community now. And this is also reflected, I think, in the number of sort of citations. So we don't have a paper yet. We're currently starting to write that and hoping to do that this summer, but we ask people to acknowledge it in their acknowledgements of their paper if they do. And you can see already we're getting, what's it, 30, 35 or almost 35 papers now have used the toolkit and acknowledged it as having done so. And there's a nice kind of growth that we're seeing. Yeah, so if you have any questions about the toolkit, the Slack channel is the toolkit Slack channel, so feel free to ask. Although it is Capra, do feel free to drop into any channel and have a look around or ask questions. There's no problem at all. We welcome it very much. Okay, so further discussion. So how's this going to work? So as I said in the toolkit meeting or the toolkit workshop, what we did is we use Slack a lot, and that seemed to be very successful. See how that works in a slightly different context. One thing I'd like to ask you to do is, if you do end up organizing a little chat among some people, do post a link into the #Capra main channel. I think a great thing about Capra is its openness. And so, if you're going to sit and have a discussion about some technical aspect of something with a few collaborators or some people who are just interested, then post a link into that channel, because many people might just want to sit in and listen. I think this is great for the younger people in the audience, just to sit and learn about something they might be interested in. So I'm going to encourage you to do that. I'm going to do the same. I'm going to post a link into the Slack channel, and that'll be where we can continue the discussions. And so I'll just quickly, I'll drop out of this and just go over Slack in case anyone isn't familiar, just to make sure everyone is comfortable. And then in a couple of minutes, what I'll do is I'll post a link, and the goal is to talk about, as I said, the faster GSF codes. What can we do to speed up our calculations? What's missing? What methods might people in the community have that we could use? Later on, in roughly, I guess, half an hour, we'll see how that discussion goes. But let's roughly time it about half an hour from now. We'll talk about covering the parameter space. Are there methods out there we should be using that we can use, maybe from elsewhere in the gravitational wave community, to help us fill out those parameter spaces in a smart way? And then finish with a discussion on fast waveforms. As I said, we'll see how we go. I think these discussions are a great tradition of Capra. There's also a great tradition of someone saying something and then just absolute silence for ages. So we'll see how all that goes. I guess before I go to Slack, does anyone at this point have any questions they'd like to bring up with everybody, or anything I've missed off, or anything they think that we should talk about as a community with first order calculations? Feel free just to put your hand up, or even just open your mic and talk. That's completely fine.
Roland, go for it.
There's a Slack channel, and I've been looking at the black hole perturbation.
Roland, you're a little quiet. I'm sorry to interrupt you. Can you speak a little louder?
I can hear you. I think that's.
So you're mentioning a Slack channel, and I've been trying to find it on the Black Hole Perturbation True Group website, but I can't really find it.
So Aaron has posted the link. The Slack channel's not. We don't have the link public, I think. I can